Hi, so following on from the previous one, just about introducing magnetic field concepts, this is about more detailed about the context you're more likely to meet in level 2 in CEA, about magnetic fields around current carrying wires and solenoids. So just a quick review, some common stuff just from last time. So magnetic field around a bar magnet, pretty similar shape to the magnetic field around the Earth. Sort of magnetic field is defined as the force on a magnetic north pole that defines the direction. The magnetic field goes from the north pole of a magnet to the south pole of a magnet, as in the top left diagram there. Where the field lines are closer together, that means you've got a stronger field. There's more force acting on the magnet. Field lines don't cross because they're representing a direction of a force. And that little weirdness about the Earth's geographic north pole is actually magnetically a south pole, and vice versa. And we measure magnetic field strength in the unit of Tesla, and magnetic toys are pretty cool. All right, but what we're going on to is looking at currents and fields. But before we get into that, we need all these relationships that we're dealing with now with these magnetic fields are all three-dimensional. Like with the electric fields and gravitational fields, the forces are in the same direction as the field. Whereas now we get situations where forces are perpendicular to fields and things. So we end up having to draw things three-dimensionally, which can get a little bit tricky. So we need because it's a three-dimensional system and we're generally drawing things on a flat 2D surface like paper, we need a system for being able to draw three-dimensional things. So we could use what we call the dot cross arrow system. Think about an arrow being fired. If it's being fired towards you, you see the tip of the arrow. We draw that as a dot, like the tip of the arrow coming towards you. If it's going away from you, if you're the one that fired the arrow, you'll see the fletching, the like feathers at the back of the arrow, which we draw as a cross. Okay, so a dot is something that's coming towards you. A cross is something that's going away from you. So some examples of what we have might use that. If we're drawing a magnetic field and it's coming towards you, now magnetic field we generally draw lots of lines. Would be like an array of dots. Okay, which would indicate, because they're all evenly spaced, that would indicate a uniform strength magnetic field within that region. A magnetic field away from you would be the same sort of arrangement, but it would be crosses instead of dots, because there's a magnetic field going away from you. We use the same system for current, except we generally draw just one, and we generally draw like a circle, sort of representing kind of like, I was thinking of it as representing the wire, and the dot represents the direction of current within the wire. And if it's going away from you, it's the circle with a cross in it, so the current's going into the screen away from you there. So we use that dot and cross method for drawing directions of currents and fields. I'm mostly going to be using it for currents in this presentation. So let's start with the magnetic field around a current carrying wire. So if we have a current coming towards you, like that, so that's coming out of the screen, towards you, the magnetic field is going to be circular around that. Okay. Now, bear in mind, anytime you're talking about a field, you need to know the shape and you need to know the direction. And there's also strength as well. We'll come back to that one in a future one. But for the direction of this, for that one, if the current is coming out of the page, it's circular around it and it's going in an anti-clockwise direction. Okay. If the current's going away from you, like that, it's circular and it's in the other direction. Okay, so going clockwise. So for both cases, you get a circular field around the wire. The direction of the magnetic field is given by what we call the right-hand grip rule. I'll come back to that in a second. And the magnetic field is stronger closer to the wire. You can see on this diagram I've actually spaced the lines closer together, closer to the wire. That's an indication that the magnetic field is stronger there. Quite often in textbooks and exams even, that's not done. Like the magnetic field lines are evenly spaced, but it is stronger nearer the wire. And the magnetic field would be stronger if the current was higher. Okay, So just a note about that right-hand grip rule, about how do we actually determine the direction of the magnetic field around a wire. We use this right-hand rule where if you imagine you're holding onto the wire with your right hand and your thumb is resting up alongside the wire. Now your thumb points in the direction of the current and your fingers will curl around the wire in the direction that the magnetic field will go. Okay, and it's just to be clear, when we talk about current there, we're talking about conventional current, not electron flow. So your thumb points in the direction of the conventional current and your fingers curl around in the direction of the magnetic field. And just, I'll say it again, pro tip, make sure you use your right hand. It's there's always people in assessments who do it the wrong way around, and you always see someone doing this with their left hand, and you just know that that's not going to turn out well. Okay, now if we take that, so that's magnetic field around a wire. If we take that another step and we talk about a loop of wire that's carrying current. So if we imagine a loop like this, we've got current going around in the loop. Now I'm going to imagine we slice through the middle of this loop and we look down on it from above. Okay, so what we're going to see is something like this, where we've got the current coming out of the screen on one side, going around and then going back into the screen on the other side. Okay, now both of those currents will produce magnetic fields, okay, both directions. So if we just look at the one on the left, to start with the current coming out of the page, if you use the right-hand grip rule, thumb coming out of the screen towards me, my fingers are curling around in the anti-clockwise direction. So that's the direction that the current, the magnetic field will go. Okay. On the other one, if I point my thumb into the screen, my fingers are curling around in the clockwise direction. So that's the direction that the magnetic field will go from there. Now, this diagram is a little bit messy at the moment, but the important thing to notice here is that in the region inside the loop, like between the wires, those fields are going in the same direction. So they kind of add together and you get a really strong field in that region inside the loop of wire. Okay. On the outside, the fields are in opposite directions. So they cancel out a little bit and you get a weaker field out there. Okay. But remember, we shouldn't really draw the diagram like this. Okay, you shouldn't have. I've drawn magnetic field lines there crossing, and that doesn't happen. So what we need to draw is really the combination of when you add those together, and that's what it looks like this. Okay, if you add those together, so we've got a region in the middle, but inside the loop we've got a strong magnetic field because the magnetic fields are from each side are in the same direction, and on the outside, it's spaced further apart because there's a weaker field there. Okay, so that's a single loop, but we don't often use just a single loop of wire. We more often use something called a solenoid. A solenoid is just many loops of wire. It's a coil, okay, which I can draw something like this. Okay, so we've got current coming out of the screen on one side, on the left, and going around and going back into the screen on the other side. So it's looping around sort of out and back into the screen. Now, the magnetic field around this is basically just a whole lot of the ones we just had added together, and you end up with a magnetic field that looks like this. Okay. Now, that should look vaguely familiar because it's basically the same as what the magnetic field of a bar magnet looks like. Okay. The only difference is with this is that you can actually access the magnetic field inside the solenoid. You can't access the magnetic field inside the bar magnet because it's solid. The magnetic field is there, but you can't sort of get to it. Okay. So we've got an end there where the magnetic field lines are coming out, the same as we have with the bar magnet, and we've got an end where the magnetic field lines are going in, the same as we have with the bar magnet. So we can talk about the north and south end of a solenoid. Okay, so the magnetic field here for a solenoid is the same shape as a bar magnet. The direction of the magnetic field is given by a different right-hand grip rule. I'll come back to that in a second. And the magnetic field is stronger inside the solenoid. That's where the magnetic field is strongest. It's stronger if you have higher current. and it's stronger when you have more turns per meter in your solenoid. So, for example, just to show you what I mean, if I had this solenoid which has a certain length and a certain number of turns, and it gives a particular magnetic field strength. Now, if I was to make that twice as long, okay, I've got double the length, but I've also got double the number of turns. So in terms of number of turns per meter, it's actually the same. So I'd actually get the same magnetic field strength out of that. It would just extend for longer. But if I did something like this, where I like double the coils over, like I wind the coils around once and then I wind another set around over the top of them, we've got the same length, but double the number of turns. So you get double the magnetic field strength in that one, okay? So coming back to that direction of the magnetic field, we use a second right-hand grip rule for this, okay? So we can draw the magnetic field something like this, okay? Now, the right-hand grip rule, so we've got the north and south, the right-hand grip rule looks kind of like this. It's basically the opposite way around than it was for the current in a wire. For the current in a wire, the thumb was the current and the fingers were the magnetic field. This is the other way around, okay? So for this one, your fingers, imagine you're holding the solenoid in your hand with your right hand, and the direction that your fingers curl around is the direction that the current is flowing around the solenoid. So you can see in that bottom diagram there, the fingers are pointing in the direction of the arrows of the current, okay? And the thumb then points in the direction that the magnetic field is going, okay? It points towards, now that's the direction of the magnetic field inside the solenoid, it points towards the north end of the solenoid, okay? Now, it's worth mentioning here that, especially if you look at that top diagram, the magnetic field, we also, like said earlier on, magnetic field goes from north to south. That's true outside the solenoid and outside a bar magnet. But inside the solenoid, the magnetic field actually goes the other way, goes from south to north, because it loops around and joins back up. Like all of those lines would loop around and join back up with the one on the other side. So it's going north to south outside, but inside it goes the other way. But with the right-hand grip rule, your thumb is pointing in the direction of the magnetic field. And again, pro tip, make sure you use your right hand, because, you know, same problem, okay? People will end up doing the wrong thing. All right, cool. That's me. Hope it helps.